Can one line follower handle both T intersections and broken lines? In this video, we are going to make the track a little more interesting than a simple loop. The mBot2 starts at the bottom of the middle vertical line facing north, so at first it just follows the line upward like a regular line follower. But then it runs into two different types of problems. First, there is a T intersection. When the robot reaches the intersection, it has to realize that this is not just a lost line, it is a decision point. Second, there are multiple broken line sections. In those areas, the robot temporarily loses the line, but it should not turn randomly or stop forever. The interesting part is that both of these situations can start with the exact same sensor reading. The Quad RGB sensor suddenly does not see a line. So the core idea is this: when the line disappears, treat it as a decision point. If the Quad RGB sensor sees the line, the robot follows the line normally. But if the sensor sees no line, the robot pauses to investigate, scans left and right, and then chooses the next action based on what it finds. So this robot is not just following a line, it is running a small decision machine whenever the line disappears. Before we get into the decision part, let's quickly look at the normal tracking behavior. When the line is visible, the Quad RGB sensor gives us a deviation value. If the robot is centered on the line, the deviation is small. If the robot drifts too far left or right, the deviation becomes larger. Then we use that deviation value to adjust the left and right motor power. This is the usual proportional line follower idea. If you are not familiar with the concept, check out the video card in the top right. In short, the base power controls the general speed, and Kp controls how strongly the robot corrects when it moves away from the line. That part runs continuously while the line is visible. But the moment the sensor says there is no line, we do not want to react too aggressively. Sensor readings can sometimes flicker for a moment, especially around edges, turns, or uneven tape. So the program first checks if the line is gone, waits for a very short time, and then checks again. In this program, that delay is 0.05 seconds. If the line comes back after that tiny delay, the robot ignores it as a glitch and continues normal tracking. But if the line is still gone, then the robot stops and starts the investigation routine. This is where the algorithm becomes interesting. Once the robot confirms that the line is truly gone, it checks both sides. First, it turns left 90 degrees and checks whether the Quad RGB sensor sees a line. That result gets saved as the left line result. Then the robot turns right 180 degrees. This points it toward the other side and it checks again. That result gets saved as the right line result. At this point, we have two simple values. Was there a line on the left? Yes or no. Was there a line on the right? Yes or no. Those two values are enough to decide what kind of situation the robot is in. There are only 4 possible combinations. If the left side has a line and the right side does not, then there is not really a choice. The robot should turn left and continue tracking. If the right side has a line and the left side does not, it should turn right and continue tracking. If neither side has a line, then this is probably not a T intersection. The robot assumes it is dealing with a broken line, so it drives forward blindly for a short distance, then checks again. And if both sides have a line, then the robot treats it as a T intersection. At a T intersection, sensing alone does not tell the robot whether it should go left or right. Both paths are valid. So in this version, the robot asks for joystick input. That means the joystick is acting as the decision policy. That is the full conceptual algorithm. When the line is visible, track normally. When the line disappears, confirm that it is really gone. Then scan left and right. And once we know whether there is a line on the left, the right, both or neither, we know what to do next. Now let's connect it to the block program. The first helper block is lineDetected. This block takes the Quad RGB sensor's line status and converts it into a simple variable. lineDetected equals 1 or lineDetected equals 0. That makes the rest of the program much easier to read because the main loop does not need to deal with the raw sensor condition every time. The next helper blocks are arcLeft and arcRight. These are small motor routines that help the robot curve back onto the selected line after a T intersection choice. Now let's look at the main loop. The main loop keeps asking one question: is the line detected? If the answer is yes, the robot uses the normal deviation-based line following logic. If the answer is no, it waits briefly and checks again. If the line comes back, it continues tracking. If the line is still gone, it stops, checks left, checks right, and then calls the GetNextStep block. So the main loop has two modes: normal tracking mode when the line is visible, investigation mode when the line disappears. The GetNextStep block is where the decision table becomes code. It looks big because there are nested if statements, but conceptually, it is just checking the four possible combinations: left yes, right no, left no, right yes, left yes, right yes, left no, right no. Each branch maps directly to one row of the table. That is why the decision table is the best way to understand this program. Once the table makes sense, the block program is just the implementation. There are also a few things you can tune. The blind drive distance can be changed if your gaps are shorter or longer. The 0.05 second confirmation delay can be adjusted if your sensor readings are noisy. The base power and KP value may need tuning if the robot is moving faster or if the track has sharper turns. And the joystick policy can eventually be replaced with something smarter, like a pre-planned route, a mission rule, or even a map-based decision. The important point is that this is not just a fixed recipe. It is a real robotics algorithm with assumptions, tuning values, and design choices. So here is the full algorithm in one sentence. When the line disappears, scan both sides and decide from the result. If neither side has a line, drive forward a short distance and search again. If both sides have a line, treat it as a T intersection and ask for the next direction. That lets one line follower algorithm handle both T intersections and broken lines with the same overall logic. I will make the full block program available in the Learn as you Explore hub. It's free to join, so sign up today and get access to the slides, code, and video for this lesson. Until the next video, check out these other line follower videos on the channel. Like this video if it helped you, share it with a friend who may find this helpful, and subscribe to the channel for more projects like this. Happy programming, and I'll see you in the next one.